Picture this, okay? You've got exactly 20 minutes left on the clock in your Physics 9702 mock exam. The pressure is on, the clock's ticking, your hand is cramping up, and you flip the page to find an extended response question all about ionic crystal structure. Now, are you ready to describe the exact electrostatic forces at play, or are you about to walk right into a carefully laid trap? Welcome to this explainer. Today we're going to decode the microscopic world of solids so you never, ever lose those crucial top band marks again.
So can you spot the examiner's three-move chess trap? See, there's almost like this hidden matrix code of repeated exam questions buried inside the Cambridge 9702 syllabus. And I'm telling you, this specific topic, it catches students completely off guard year after year. It leads to instantly lost marks, massive grade boundary risks, and a huge confidence shock right when you need your absolute best focus.
Section 1. The examiner's hidden trap. Why ordinary revision fails.
Right, so here's the thing. When studying the broader chapter on crystal structure, a lot of students just rely on rote memorization. There's a massive disconnect happening here. See, a teacher's explanation focuses heavily on intuitive understanding. They want you to really get why a grain of salt shatters if you hit it with a hammer. But the examiner's mark scheme? It is ruthlessly focused on precision. They honestly don't care about a story about a hammer, you know? They're looking for highly specific, disciplined phrases, like the repulsion of like charges along cleavage planes. That right there is the gap between general understanding and the exact wording an examiner actually rewards with marks.
And this leads us to the single most painful learner mistake. So many students just drop a scientifically correct term, like ionic bonding or crystal lattice, and then they just stop writing. They completely fail to explain the underlying microscopic basis. What they're missing is describing that an ionic crystal is a giant 3D lattice held together by strong electrostatic forces acting in all directions between oppositely charged ions. By failing to describe what's physically happening inside the solid, they're literally leaving the most valuable marks on the table.
Section 2. Inside the ionic crystal. From macro to micro.
Okay, let's dive into this and get you your first really quick win. We actually need to completely reverse how you think about this topic. Instead of starting with invisible atoms, we're going to work backward from the macroscopic observable phenomena straight down into the microscopic picture. Ionic crystal patterns are all about interpreting how a solid behaves based entirely on its internal arrangement at the atomic level. Just imagine a massive, perfectly ordered, alternating grid of positive and negative spheres locked tightly into place. The solid's macro behavior, like its really high melting point or its brittleness, is completely controlled by this internal atomic packing. If you shift that internal arrangement even slightly, you fundamentally alter how the solid behaves out in the real world.
Now, I'm going to make you a promise. In just a moment, I'll show you the exact examiner clue that saves a failing answer in 60 seconds flat. And I promise you, this clue will completely change how you write your answers. But first, you absolutely need the structural framework that makes that clue obvious in the first place.
Section 3. High-mark answer framework. The four-part survival sequence.
All right, let's look at how this builds into the absolute safest paragraph structure to secure those top band marks. This right here is your ultimate survival sequence for the exam room. Step 1, definition. You've got to start by clearly defining the structure, like stating it's a regular lattice of positive and negative ions. Step 2, mechanism. Here's where you explain the actual physics, like the strong electrostatic attraction holding them all together. Step 3, consequence. What does that mechanism result in? Well, a high melting point, because a large amount of thermal energy is required to break those bonds. And finally, step 4, application. Where is this used in the real world based on that specific consequence? This exact sequence needs to be your anchor.
Layering this into your Cambridge exam strategy, we can translate those steps into actionable writing goals. You move from the core concept, like electrostatic forces, and back it up with evidence, such as the melting point data they gave you in the question. Then you apply your scientific reasoning to link the two together. And finally, package it all perfectly using the examiner wording. You literally must connect the physical cause and effect directly to the language the examiner is specifically requesting.
Section 4. Flawed versus top band answers. Spot the error.
Now let's put this framework to the test with an interactive 1-minute rescue challenge using a real student's answer. Take a look at this typical flawed answer. Ionic crystals are strong because of ionic bonds. This is why they are used in technology. Okay, I want you to pause for a second. Really think about that four-part survival sequence we literally just covered.
Can you predict why this answer completely fails the Cambridge mark scheme?
Did you spot it? The core issue here is the complete lack of a link between the application, which they just vaguely stated as technology, and the microscopic reason. I mean, sure, it mentions ionic bonds, but it explains absolutely nothing about the mechanism or the atomic arrangement. The marks just evaporate because that physical, microscopic connection is entirely missing.
So the examiner style correction requires total precision. A top band answer replaces those vague facts with a highly disciplined connection. It explicitly defines the specific atomic packing, the regular alternating three-dimensional lattice of oppositely charged ions, and it directly links it to the material's defect tolerance and field response. It perfectly connects the microscopic structure to the macroscopic consequence. That is how you win those points.
Section 5. Real-world physics applications. Why this matters.
Examiners absolutely love it when you ground these microscopic concepts in tangible, real-world technologies. It shows total mastery of the topic. To truly impress them, you've got to use precise, correct examples. Throwing in applications like piezoelectric sensors, solid-state electrolytes in batteries, specific high-strength ceramics, or gemstones, that proves you really get the physics. For instance, if you explain how the rigid ionic lattice in a solid-state electrolyte actually allows specific ions to hop right through the structure while maintaining its overall mechanical strength, wow! That shows you understand exactly how the specific crystal arrangement controls the material's real-world performance.
As you're studying, I want you to use these exact memory triggers. What changes inside the solid? And what can we observe outside the solid? If you can answer those questions out loud, linking the invisible lattice to the observable physical properties, you'll be able to pull this entire physics framework directly from your memory, even in the super high-pressure environment of the real exam.
Section 6. Next exam survival step. The binge loop transition. Okay, we've successfully built your 1-minute rescue kit for the physics concepts, but the matrix code of the Cambridge exam has one final, very dangerous trap waiting for you. Here is the exact curiosity gap we're left with. You now have this perfect physics framework, right? But what happens if you misread the examiner's specific command words? Let's say a question asks you to describe an ionic crystal. Well, you just need to state it's a regular 3D lattice of alternating ions. But what if the command word is explain? Now you must add the mechanism, due to the strong electrostatic attraction between oppositely charged ions in all directions. Look, even with absolutely perfect physics knowledge, if you answer a describe question with an explain framework or vice versa, you still lose the grade. This is an unresolved problem you've absolutely got to fix. To get the full, top-band evaluation framework, you really need to take the next step. Seek out materials that explicitly decode those specific examiner report mistakes and command words. It is incredibly crucial for your revision strategy to understand precisely what language the examiner demands for every single command.
Once you combine the physics framework we just went through with a total mastery of command words, you will finally achieve checkmate against the exam board. But the ultimate question is this. The next time you open up that exam booklet and see a microscopic structure question staring back at you, are you going to freeze, or will you use this 4-part framework to absolutely secure your grade? Good luck out there, and keep explaining the world around you.